Okay, coordination compounds. Transition metals tend to form complex ions. In a complex ion, and we did have an introduction to this in an earlier chapter, you have a central metal ion that has one or more ligands attached to it. It's not an ionic compound because it is an ion. It still has a charge. So here we have an example where there's a cobalt 3+ ion, and it has 6 ammonia molecules bonded to it. So that's the complex ion. If you make a compound, so you've got a complex ion and then you need counter ions. So if we take this complex ion, which has a positive 3 charge, and we put 3 chloride ions with it, there's our lowest ratio to form a neutral compound. Together, that's called a coordination compound. These are the counter ions, and this is the complex ion. The ligands here are Lewis bases, and they form a bond with the metal. We'll talk more about the Lewis base thing in a minute. So that metal ion has 2 types of interactions. We call them valences. There's the primary valence, which is the oxidation state on that central metal ion. And then there's a secondary valence, or it's often called a coordination number. That's how many molecules or ions, how many ligands are bound directly to the metal. So Werner, the guy whose quote we had on the opening slide, did a lot of work with cobalt coordination compounds. At that time, though, they didn't really know exactly what they were, so they were, investigating how are these things put together. So originally, the formula shown here was written as a cobalt 3 chloride dot 6 ammonia. So the format of the formula was like a hydrate, except it was ammonia instead of water. We now write it this way, understanding that this is a complex ion of cobalt with ammonia molecules and 3 chloride counterions. So let's look at this formula and identify what's the primary valence, the charge on the cobalt ion. It's +3. So we're going to figure that out by looking at the charges on the ligands. Here, the ligands don't have any charges. And then we're going to look at the counterions. We've got 3 -1 ions. This whole thing's neutral, so the cobalt must be +3. The secondary valence is how many ligands are attached to the cobalt? 6. There are 6 ammonia molecules attached to the cobalt. So the complex ion has brackets around it, and the counterions on the outside. There are other variations with the same chemical formula because the chloride can replace ammonia as it can either be the counterion as we see it up here, or it can be one of the ligands. And so you can have cobalt with 5 ammonias and 1 chloride as the ligand and 2 chlorides as counterions, or you could have 2 chlorides as ligands with 4 ammonias. Lots of variations. So a complex ion is really a Lewis acid-base adduct. Yeah, question?
I'm sorry, about the other one, the variations. Would that then change the primary valence?
That's a good question. Would that change the primary valence? We still have 3 chlorides, right? And overall a neutral charge, and the ammonias don't have a charge. So the primary valence is going to be the same.
Okay, and then the secondary.
And the secondary valence is also the same because here there's 5 + 1 is 6, and 4 + 2 is 6.
If it wasn't a neutral molecule, where would the charge be?
Well, where the charge is, so the complex ion is what has the charge. That's the complex ion. And that combines with 3 chlorides to form a neutral compound.
So the variations, they're just the chloride's just for replacing the ligands.
Yeah.
So
So here, yeah, the ammonia is just not there anymore. So if we look at those complex ions, the charge on the ion is going to be different. This one's going to be +2, and this one's going to be +1. The charge on the cobalt ion inside is the same. So a Lewis acid-base adduct. An adduct is when you have 2 molecules or ions that come together. It's a chemical reaction. They bond together, but you don't lose any pieces. It's just like taking these 2 things and sticking them together. Most chemical reactions do not form adducts. You know, they come apart and get put back together in different ways. This is just taking those 2 things and sticking them together. And the bonds form when the ligand donates a pair of electrons to an empty orbital on the metal. It's called a coordinate covalent bond. The electrons are coming from one atom, and it is a covalent bond. So here we can look at a silver ion and ammonia molecule. So this is acting as a Lewis base. A Lewis base is an electron pair donor. And so we see the nitrogen here. It has a lone pair. And it's that lone pair that nitrogen is going to share with silver. And silver's fine with that because it's got a bunch of empty orbitals. Like, yeah, you can put your 2 electrons in my empty orbitals, and then we'll be good friends. Right? And so you get a covalent bond forming over here. Now, there, coordinate covalent bond. And then another ammonia can come with its lone pair of electrons and also share with the silver. And then you've got complex ion. Now, why is it 2 ammonias and not 3 or 4? Well, at this point, we're not going to worry about that. But ligands are good Lewis bases. They're going to have at least 1 lone pair. These are some common ligands. Water is a common ligand. Yeah, stupid thing. Up here, water. See, water's got 2 lone pairs. So it could take one of those lone pairs and make a coordinate covalent bond, say, with ammonia. No, I mean aluminum. We saw that in an earlier chapter, right? Aluminum making these complex ions. Ammonia is another one. The chloride ion. Carbon monoxide. Carbon monoxide can do this. Cyanide, thiocyanate. We used that in our qual scheme the other day. This is the oxalate ion. That shows up a lot as well. This one's called ethylene diamine because it's got 2 carbons here in the middle. So that's the eth prefix, and then it's got 2 amines on it, so it's ethylene diamine. And then there's this one. This one's really nice. Ethylene diamine tetraacetate, usually called EDTA. And you may have heard of that. You may, if you read labels, you might have seen that. It's a very common ligand. So in these coordination compounds, we can divide those ligands into different groups. So a monodentate ligand donates 1 pair of electrons to the central metal. So something like ammonia or water is going to donate 1 pair of electrons, and it's just going to form 1 bond. A bidentate ligand donates two pairs of electrons, and they are from different atoms within the ligand. So here's ethylene diamine. This nitrogen can donate its lone pair, and the other one can also donate its lone pair. So you look at water and you say, oh, well, it's got two lone pairs. Yeah, but it's only going to donate one. The bidentate is from two different atoms. So oxalate will do that, and we often abbreviate oxalate as OX. Ethylene diamine can also do that, abbreviate that as EN. And then polydentate ligands can donate more than two pairs. And again, each pair is coming from a different atom. So ethylene diamine tetraacetate ion can actually donate, waiting for screen, great. No, okay. It can donate six electron pairs. So here's EDTA. So there's a lone pair here and here, the nitrogen, the other nitrogen, and these oxygens over here. They can all donate and complex a single ion. So here we have what that might look like. Here's a cobalt-3 ion with one EDTA ion complexing with it. And so we've got multiple coordinate covalent bonds between the cobalt and this one large ligand. So it wraps around the metal and completely covers it up. Here's cobalt with 3 ethylene diamine ligands around it. So we call this a chelate, a complex ion that has a bidentate or a polydentate ligand in it. So both of these would be chelates. Ethylene diamine and EDTA are chelating agents because they form chelates. Any questions? Chelating agents are really useful because when you chelate an ion like this, it's generally going to be soluble in water. So some things that would normally not be soluble, you can make them soluble by adding chelating agents. And that's what some cleaners do. They have chelating agents in them, and they help to get the calcium and the magnesium that form the soap scum and the hard water stuff off your bathroom fixtures. So the coordination number can vary from 2 up to 12, but 4 and 6 are the most common. With +1 ions, you will sometimes see just 2. Sorry, I'm having some issues here. So you may, fine. You may have a coordination number of 2 with the lower oxidation state ions. 6 or below for the first row transition metals. The higher, what would you say? Well, they are bigger. The larger ones would have 6 or higher. You can have odd numbers of ligands, but that's rare. The geometries, these geometries should look familiar to you from Vesper theory. So the geometry is going to depend on the coordination number, but it's also going to depend on the number of d electrons in the metal ion. So it's not always what we expect. But here, iron with 6 water molecules as ligands is going to form an octahedral structure. Palladium with 4 chlorines is going to form a square planar. And yet zinc with ammonia is tetrahedral. And the difference here is because of the number of d electrons. So how do we name these things? So this is a system originally proposed by Werner, and it's just a set of general rules. You guys have gotten this far. You can do this too. It's not that bad. So you name the ligands. So the neutral ligands tend to just have whatever molecule name as their name. Couple of exceptions. Water isn't called water, it's called aqua. NH4, ammonia, is called amine. And CO, which is carbon monoxide, is called carbonyl. So those are special names. If you have ligands that are anions, you're going to take the name of the ion and you're going to modify the ending. So if you have chloride as your ligand, we change that "ide" ending to O. So chloride becomes chloro. If it's sulfate, it becomes ado, or ato, sulfato or sulfato, potato or potato, whichever. Sulfito, right? They sound a little ridiculous, but we're changing the endings so they have O's on them. It's like making adjectives out of words that were originally other parts of speech. And we'll see in table 25.4, there's other names of common ligands. So then you're going to list the names of the ligands in alphabetical order, and those are going to come before the name of the metal ion. So we would list amine before chloro, because A comes before C. We use a prefix to indicate how many ligands of each kind there are. So familiar prefixes here: di, tri, tetra, penta, or hexa. We're not going to get any larger than this. So if we see trichloro, that means 3 chloride ligands. Tetraamine, tetra meaning 4, amine referring to the ammonia molecule. What if the name of the ligand has prefixes, like ethylene diamine? Then what we're going to do is we're going to put parentheses around the name of the ligand and use the second group of numerical prefixes, bis, tris, or tetrakis, right, to indicate how many. So this is tris ethylene diamine. Tris meaning 3. We're not using tri because ethylene diamine already has a prefix inside of it. The numerical prefixes do not change the alphabetical order. You're looking at alphabetically the name of the ligands without those prefixes. So you have the prefixes in order with all their, not the prefixes. You've got the ligands with their prefixes, all of those listed first, then you name the metal. So if the complex ion that you're naming is a cation, you just use the name of the metal followed by the oxidation state written with a Roman numeral. So in cations, CO3 plus is cobalt 3, PT2 plus is platinum 2, etc. So if the complex ion is an anion, then you're going to change the ending of the metal's name to 8, and again include the oxidation state. So cobalt becomes cobaltate 3. Platinum is platinate 2. Some of the metals are going to use the Latin names. So copper is cuprum. So instead of copperate, it's cuprate. The good news about this chapter is the exam is a take-home exam, right? So you don't really have to memorize all of this stuff. You just have to be able to look it up and do it. Yeah, just, that's all, right? Okay, so then you put the whole complex ion name together. You list the ligands first, followed by the metal. Okay, so here, PT NH32Cl4 2 minus. That's diamine tetrachloroplatinate 2 ion. So, you read off long words like that and people are like, oh my goodness, you're just amazing. It's prefixes. That's all it is. So here we got this one. So that one's hexamine cobalt 3. This was platinate because it's an anion. This is cobalt, not cobaltate, because it's a positive ion. So when we did ionic compounds back in the simple days of Chem 1A, right, the cations were almost always a metal, right? And the metal may have had a numerical, Roman numerals for its charge, but you didn't mess with the name, right? But the anions, like chlorine becoming an ion, you change the ending of the name. So anions always get the ending of their name changed. That's partly why I think of metals as being masculine and nonmetals as being feminine. So, we're talking highly traditional stuff here. So traditionally, the woman would change her last name. So the nonmetal, being feminine in Mrs. K's chemistry land, changes the ending of her name, right? And the metal doesn't. And so we're following that same pattern here. We're trying to be consistent. So here are some of the names. So some common ligands. These are anions. And so the endings of their names get changed when we put them into the complex ion. Here are neutral molecules. Those 3 have special names, and then there's ethylene diamine. And then these are the names of some common metals when they're found in anionic complex ions. So this is where we change the endings of the names. So chromate, cobaltate, cuprate, orate, ferrate, plumate, those are all the Latin. Manganate, molybdate, nickelate, platinate, argentate, stannate, those are both Latin, and zincate, right? Yeah, they look weird. They are weird. Okay, so those are the complex ions, and then to have the coordination compound, you've got the complex ion and you've got the counter ions. So this is overall, this is writing the formula. Back it up. Writing the formula, you write the symbol for the metal first, then you write the neutral molecules, and then the anions. And then if there's more than one neutral molecule or anion, you list them in alphabetical order based on the chemical symbol. So alphabetizing and counting, right? Yes, I can go back. So if you have, you put the neutral molecules first, and then the anions. If you have 2 different anions, you put them in alphabetical order by the symbol name, not their actual name, right? So silver has the symbol Ag. It wouldn't be an anion, but if it was, right? So you'd alphabetize it by the chemical symbol, not its name. So let's practice. Whoops, that's not what I meant to do. Very expressive size. So here we have, in the brackets, is the complex ion. So what goes first? Does the metal go first? No, the metal goes last. The names of the ligands in alphabetical order by their names. So CO, maybe let's just write these down, right? CO is called what? Carbonyl. How about NH3? You know what that one's called? Amine. So, which comes first in the alphabet, A or C? A. Okay, so we're going to list amine first. How many amine ligands do we have? 5. Okay? So 5 would be pentaamine, and then carbonyl, and Mn is manganese. And what is the oxidation state of the manganese? 2. So this is sulfate. Sulfate has a -2 charge. Ammonia and carbon monoxide are both neutral, right? So then the manganese must be +2. So we've got pentaamine carbonyl manganese 2, sulfate. These are a little harder to Google, right? Okay, let's look at this one. The complex ion, is it a cation or an anion? It's the anion. So we're going to list the name of the cation first, which is sodium. And then we need to name that complex ion that's the anion. So it's got chlorides as its ligands. What do we call those? Chloro. And there's 4 of them. Tetra, chloro. PT is platinum, but we have to change the ending of its name, right? Platinate. And then we have to figure out what its oxidation state is. Not 4. Okay, so we have 2 sodiums. They're each +1, right? We have 4 chlorines. They're each -1 chlorides. So the platinum is +2. Any questions?